into what is expected of you in the control lab. I know you already have an idea of what goes on in that lab, because last year we did a similar thing with a different set of laboratory experiments. And I think we were there physically, but because I am not available, we have to do this in this format. So please bear with me. I'll be very brief just to update you in regards to what we expect you to do this semester in the lab. After all, I already know that this is the last group in the lab, and so you've already had experiences elsewhere in different labs. And so this should not be very difficult, because you already, I also want to believe, learned a few of the concepts that you will need in this lab. So allow me to share my screen so that we are able to, introduce this in a proper format. So now, I know you've been provided with lab manuals from Alice, and she has given you a set of 3 in 2. That means there's a lab that has 2 manuals, but it's a similar experiment. And then, of course, there's the second laboratory, which is on the traffic lights. So I need to introduce you to these 3 labs, which are basically 2 lab experiments, because 2 of them are really 2 manuals are simply the same thing. But I need to sort of give you a guideline in how to prepare adequately for this lab, so that when you begin, you will have a good run. All right, I think the best way to start is just to let you know that, of course, to just check with you, you already have a manual, actually 2 manuals on PID control. We are going to be very specific with them. I think one is 11 pages, the other one is 14 pages, I hope so. And then you've got another manual, which is on the design of traffic lights, which basically, as you are aware, is a continuation of what we were doing in the last semester. So you're simply probably advancing yourself in regards to your design. So in the last semester, you were being introduced to the basic principles of PLCs, but now you're actually doing a design of an actual application. So I think the best way for me to do this is to have a proper introduction with you. And so I'll just call this a brief introduction, industrial automation. Industrial automation. Please, again, just confirm with me that you can see my screen. I did not check that. Just somebody tell me you can see my screen, please.
Yes, we can see.
Oh, thank you. All right. So now, in the world we live in, ladies and gentlemen, you must have noticed, especially in this generation, that there's a lot of automation that's going on. And it covers a large area of human, or a large aspect of human living. So be they at home, at school, wherever you'll be working at, there's a lot of automation going on. But then there's also automation on industrial level. That is, the scale is larger than what you'd expect in an ordinary setup. And there are several techniques or technologies that have come up to enable automation to occur. Now, in control systems, which is, I think, 4th year, yes, we introduce certain aspects of these technologies that we use to achieve industrial scale automation, so that we are able to increase our efficiency as human beings, so that we are able to improve on our safety. That means we minimize our interactions with equipment, and so that we are also able to scale up our production or productivity, so that we can do things in a larger scale than we could do without automation. Now, there are several tools that are used, but the one that I'm going to discuss here, because of time, are to achieve automation, we use SCADA systems. We also use DCS systems. I'll tell you about that. We also use HMI systems. We also use PLCs. We also use PIDs. I know all these are abbreviations, but you can check them out. Now, the largest way of managing or monitoring an automated system, like an industry level, is to use SCADA systems, which just stands for supervisory control, because it's used for control, and data acquisition. So I know you'll go for fourth term, you'll go for industrial attachments. You will see that in most companies these days, they've got this room they call a control room, where they're able to control and monitor systems that are downstream on the floor, but from a remote location. So they're able to start a pump remotely. They're able to check the flow of steam or water remotely. They're able to do a lot of things remotely, so that they limit their interactions with equipments, because either those equipments are very dangerous to be around, or the environment around there is not suitable for human beings to be exposed to. It could either be too cold, it could be either too dry, it could be either too hot, maybe it's too wet, and all that stuff. Then this is like the largest form of management or automation. The largest automation control is through SCADA systems. This you'll see in the industries. Then I think this is distributed. I think it's, I don't know. Please just confirm. You will check it again. Communication systems. I don't know whether it's communications or control. I'm not too sure. I think it's distributed control systems, where you are extending the level of management of your automated system. That means if you're working at Kenya Pipeline Corporation, for example, we know that they pump fuel from Mombasa to Nairobi through the pipes. So they can have a DCS, that is a distributed control system, in Mombasa, but they're able to control systems along the way, because there are sensors connected to those pipes and all that stuff. There are actuators all over. So they're able to connect and control systems all the way to Nairobi. So because this extends a larger geographical, because this is usually sort of in one place, okay? But this is extended to a larger geographical setup. That's why it's called distributed system. Of course, you know about HMI. These systems usually come with human-machine interface, because then that is how you're able to see what you're doing and also interface and also type in commands. So it comes with a screen. So sometimes somebody works with a device that they're able to use to control an equipment, more like what you hold on to when you're playing video games, or what you hold on to when you're piloting a drone, or just controlling a device remotely. Of course, these two are the ones that we are now discussing, because these ones are large scale. It's very difficult to set up a laboratory for you to manage this. But please remember, SCADA systems consists of all these. SCADA systems contain HMIs, they contain PLCs, they contain PIDs. So SCADA system is like a general way of controlling the entire industry that is automated. So in our labs, what we could bring to our scale, and so that we understand these concepts, is PLCs, which is programmable logic controllers. Programmable logic controllers. I am very sorry that our course outline or your course is not configured correctly. PLCs is an entire topic, an entire unit, not even a topic, an entire unit to be discussed in 5th year. And actually, that's what we're doing with the 5th years currently, 5th year, 2nd semester. Unfortunately, the lab is done in 4th year, 1st and 2nd semester. So if it were me, I would have probably had the course done in 4th year, that is PLCs, and then the laboratory is done in 5th year, because then now you would have mastered the principles of PLCs. But be that as it may, I know you were able to adjust yourselves properly. And of course, now this I want to believe you have done in 4th year. I don't know whether you did it in first semester or this semester, but you need to have done this by now. Proportional plus integral plus derivative controllers. So these two are the ones that we are actually trying to work around this semester. These two, very important, PLCs and PIDs. So please note that we are discussing these as tools that are used to achieve industrial automation. Last semester, you remember we were looking at the technologies that we use to achieve control of systems, whether they were pneumatic, and stuff like that. But this time round, we are looking at technologies that we use to achieve automation in the industry. So PLCs and PIDs will form the integral part of our discussion. So I want to start very quickly because we don't have a lot of time with the first one, which is the PIDs. Now, please note that, sorry, let me do it elsewhere. Yes, let me use this PID control. So if you have discussed this before, and I want to believe at this time you should have discussed feedback systems, we know that PIDs can be a very, very important way of controlling the plant system, or what we call the industry that we are in, if we put it as a block diagram. The thing is, the world we live in is not linear. It is non-linear. But most of the modeling that we do in class is for linear systems. That's why in control systems, you did linear time invariant systems. And the reason for that is because modeling linear systems is easier mathematically. You can mathematically represent them either through the use of Laplace transforms, Fourier transforms, Z transforms. I don't know whether you've done Z transforms. If you haven't, then you'll do them in next year. But anyway, what I mean is we have a lot of methods that we use to mathematically represent linear systems. Okay. Unfortunately, the real world is not linear. So we must try and accommodate the non-linear effects of the systems, especially the control systems that we deal with in the industry. So to accommodate them, the non-linear effects, we bring in some of these things like PID control. And you will see in a short while and through your labs how you can use these PID control tool to help design systems, control systems, and adjust them accordingly to achieve a desired objective. Okay, so typically a system that you have, I don't know, the feedback system, and I'm going to use a unity feedback system here for ease of illustration. We know that most of the examples we do in class are just unity feedback systems. So that's what I'll try and do. So typically in a linear feedback system, we usually call this, I think, R of t, and then this is C of t. I'm putting it in the time domain. And so this is usually our controller, and this is our plant. This is the error signal, and of course, this is the output of the controller. Please note the arrows are very important because this is a feedback system, a unity feedback system. Let's denote the controller with C of S, and this is capital now because that's a frequency domain. I've just mixed frequency domain and time domain, but anyway, you'll understand. You probably have been explained to that. The reason why we introduce controllers in control systems or into our plants is because most of the plants that we deal with, or plant systems, they're already installed and they are fixed. If they are motors, they're already fixed in the plant. You've already bought them, installed them, If they're generators, they're already fixed. If it's a filling machine, it's already fixed, okay? But in order to change the performance or to change the characteristics, which is usually probably the most important one, is the performance characteristics of the plant. Because you cannot uproot the plant and bring in a new one with the new specified performance specifications, the best way is to introduce a controller so that the adjustments that you want to make, you make them on the controller. But then because the controller is cascaded with the plant system, then the controller will effect those changes to the plant. So every time you don't have to change the plant system. All we have to keep updating or changing is the controller system, because it is the controller system that we can easily adjust and replace accordingly. So when we change the characteristics of the controller, we inherently change the characteristics of the plant or the performance of the plant. And that is what I intend we expect you to study in these labs that we are going to do. Now, in PID control, you can see that you can sort of write a mathematical equation in the time domain to represent this controller, okay? So for example, to get the output of the controller, I'm only interested in the controller part, not the entire feedback system, just the controller part. That is the relationship between U and T, I mean U of T and E of T, okay? So U of T could be either for a PID system. This is for a PID because that's what we are discussing. In class, you would have probably discussed proportional on their own, integral on their own, derivative on their own, and then you discussed the combination. But if you can remember, the equation for the PID controller is this. Very, very common. This should be in the back of your head. This is KD because KP, KI, and KD, because I'm using different KD, and then these are derivatives, so it's going to be the E dt. Okay, so you will see here, therefore, that we use this equation to represent the time domain for a PID controller, where U of T is the output and E of T is the input of the controller. But in the essence of the feedback system, it is the error signal. Okay, so this, because I don't have time, is the proportion. We call it the proportional constant. The proportional constant. This is the integral constant. And of course, we've got the derivative constant. Ladies and gentlemen, I have told you very clearly so that because the plant system is fixed, it is the elements or the variables within the controller that we can adjust in order to affect the performance specifications of the plant. Now, there are two performance criteria or two performance, for lack of a better word, two performance metrics that we use. We always look for the transient response, or we look for steady state response. I'm trying to just summarize this so that when you study, you have a clear picture of what is expected of you. So therefore, what we mean by this is you need to see how you can change things. Like for those, you must have done transient response and steady state response. If you haven't, then you need to go back to third year. But what I'm trying to say is, in order to change the parameters, the performance specifications of the plant, we always characterize the plant. We plot its performance in a graph. And you're going to use MATLAB or Octave, which is a free version of MATLAB for those who can't afford a purchased version. But we'll use MATLAB to be able to plot the characteristics of the plant system, and then we'll be changing the variables of the controller, and we see how that changes the performance of the plant. That's what we'll intend to do. And so we'll be interested in things like rise time. If you remember your transient response, we'll be interested in things like overshoot. You will be interested in things like settling time. What else? In steady state error, we'll be interested in things like the steady state error. I mean, steady state response will be interested in the steady state error. So you always want systems that have a certain rise time. You don't want the overshoots to be too high. What I mean is this: you don't want a system that takes too long to settle, like that. It has a longer settling time. So we want systems with a shorter, less settling time, because the faster it settles, it means the faster the system becomes steady. So it's predictable. But when there are these oscillations at the beginning, then the system is very unstable. And so it's difficult to control. In control systems, we want to achieve stability as soon as possible. So you actually need a shorter settling time. That is what we strive to get. We need a shorter overshoot, or a small overshoot. We need the rise time should not be very high. Okay, should be an adequate rise time. I don't know what values we'd be looking at. Some of this you'd be asked to adjust on your own and figure out the best response you can get. Okay, so you need to change these things. So in order to effect changes, effect how the rise time, because MATLAB will be giving you these figures, but you need to adjust so that you have a system that sort of is like this, that settles almost immediately. Okay, so maybe the rise time is a little average and then it settles almost immediately. So therefore, you will have to be adjusting the values of Kp, Ki, and Kd. So once you change the values of Kp, Ki, and Kd, you will see the effect on the rise time, the overshoot, the settling time, and the steady state error. So that is how. So if your system, for example, has a very high rise time, if you want to decrease it, then you add the proportional constant. Then that value will be reducing. So in your labs, there are two experiments for the. I think I thought I had them somewhere here. Yes, there is the PID controller design and the PID control using MATLAB. So because of time, I'm just going to ask you, ladies and gentlemen, one, you have to start with the PID controller design, the one for 11 pages, because it is the one that leads you to the PID control using MATLAB. So you start with the first one, complete it. It's very easy to follow because it teaches you these concepts that I've been telling you about here. And it gives you even the code to enter. So you don't even have to think of a code. It tells you, this is the transfer function of our system. Please enter this code in MATLAB. Then all you have to do is observe and draw or plot, check the plot, okay? And once you do that, you will be seeing the different effects of increasing and decreasing the values of Ki, Kp, and Kd. And you will see that by increasing Kp, Ki, and Kd, you will be changing how the graph appears, up to a point where you will see a graph that is considered the best in terms of achieving stability. Okay, so now you will just follow those instructions as they are. In fact, there is nothing much to do with the PID controller design except follow the procedure as put in your manual and put in the commands as put in the manual, and then observe and plot your graphs. Of course, the graphs will be plotted. So these days, I think you'll have to download them or save them somehow, because you'll have to paste them on in your manual, in your lab report. What I'm interested in emphasizing is the PID control using MATLAB, the 14-page document, because then it is an elevated version of the PID controller design, the 11-page version. Because now here, you're going to do your own unique design, because there's no way. This is where I don't expect students to have the same report or the same results. I don't expect that, because here everybody is doing their own design. What I have done is I have put as an appendix a very good illustration of how to do what we call parameter tuning, because that's basically what that lab is all about. It's all about parameter tuning. And parameter tuning is the design. That's the design, because you're simply figuring out the optimal values of Ki, Kp, and Kd that will give you the best response, the best transient response, and the best steady state response. So here you will be either increasing or decreasing values of Kp, Ki, and Kd. You will already in your manual see that you have been given a general effect of Kp, Ki, and Kd on both the response time, transient response and steady state response. So you will know that if I want to increase the overshoot, I simply increase my integral constant, then the overshoot would become higher. So you will be able to see that, but you'll have to decide on the figures on your own, because now you'll be told start with Kd is 400. So you'll have to adjust this value. You pick values either higher or lower depending on what you want to achieve. And this is where I say there's no way people will have the same values in their manual. If you do have same values, then you're simply copying. So the second lab is where you have to take your time and follow the procedure that I've given in the appendix. I did that intentionally, not so that it guides you on how I expect you to do your own work. So there's an example of how the work is done in the appendix, step by step. Step number 1, do this. Step number 2, do this. The example is illustrated. So you will be able to see what that example achieves at the end. And then now you do your own based on the question that is posed to you. So please take your time with the second part of this experiment and start with what is at the appendix. Try and look at that example and understand it, and then follow the same steps while you're doing your own parameter tuning to achieve the desired goals that are put, or the objectives that are placed for you in the manual. I have also included how I expect the lab report to be written for this kind of lab. So you will see the structure of what you need to include in your lab report, because I know most of the observations would be made on MATLAB, and you'll have to just download or save the plots, and then you will of course paste them in your document. But there's a structure of how the lab report should come out, and so that should guide you properly. So because we've spent 30 minutes already, I want to move on to the second part of the lab. Let me just mention at this point that this lab, I'm trying to look for it, yes. This lab should take you less than 30 minutes for any serious students, because you're simply following a procedure. It might take you longer if you haven't encountered MATLAB or Octave for that matter, but if you have, then it should take you less than 30 minutes. But you have 2 hours, is it not 2 hours, 3 hours to complete it. You need to prepare adequately. The other beauty is you can do it at home. If you have MATLAB installed in your computer or Octave installed in your computer, you can also try it at home. You'll still achieve the same results. If not, you're expected to do this lab in the computer lab, the one where Mr. Waweru sits. That's where you're expected to do this lab. And then during the second session of your lab, you'll be expected to do PID control using MATLAB. Again, you can do it at home, or you come do it in the lab as is expected, but you have another 3 hours for you to do it in the lab. So you can decide that you're going to do all of them in one lab, depending on how well you understand MATLAB and how well you already have understood PID control. So I expect you to do adequate preparation, where whenever there is a place where you are asked for a homework, please do that homework and include the homework in the lab report. So if the lab report gives you a homework, do it and include it in the lab report. I hope that is very, very clear. So that's on PID control. If you have any issues during your lab or while you're preparing for the PID control part, you can always email me. You now have my email address, and I will try as much as possible to assist however I can. So please do that. So now I'll move on to the next part of the lab, which is very, very critical, though it is a continuation of the first semester, but I told you it's the most engaging lab that you'll attempt this semester. So, and that is PLCs. I will not discuss what PLCs are because we have done this before. However, I know that some of us probably have forgotten. But if you can remember, PLCs are like industrial computers. Okay, they have various inputs, they have various outputs, but we use them to control and monitor industrial equipment. But that is based on a specific programming that we were calling ladder logic. So we were actually coming up with ladder diagrams. Okay, if you can remember from your first semester. So PLCs, by the way, come in very different sizes. There are PLCs that are very small. They can even fit your pocket. But then there are others that are also very large and heavy duty. So they are mounted on racks. So if you go to the industries, you'll find like a room where it looks like a server room, but it's just consisting of PLCs because they are mounted on racks. Those are heavy duty industrial scale PLCs. We agreed in the last semester that PLCs are used often because, of course, they mimic, they're just computer systems, but they cannot be compared to the ordinary desktop or computers that we interact with. Why? Because one, they're heavy duty. They are able to survive very harsh conditions. You can put them in stormy weathers, you can put them in snowy conditions, you can put them in dusty conditions, you can put them in hot conditions, steam conditions, and you can put them in all those very, very drastic environment conditions, but they are able to withstand that environment and work. They are modular in nature. They've got modules. You remember we discussed them before. You've got the CPU, just like a computer. You've got the input-output devices. You've got memory systems, you know, but these ones are customized so that they achieve specific functions. They are functions that do the communication. They are functions or modules that do the display part. They are functions that do the input-output devices, and so on and so forth. And they're used for several industrial applications. So PLCs by now should not be strange. Okay. For those of you who are struggling with PLCs, I'm going to give you a very good help at the end of this class because it's a very, very interesting area. And you'd like, if for those who would like to pursue it, I'll give you a guide. Now, I have told you that if you go to the industries, you'll find SCADA systems, but within those SCADA systems, you'll find PLCs, you'll find human machine interfaces, you know, you'll find PIDs and so on and so forth, okay? But what we want to do is to design a PLC, program. So you're actually going to come up with a ladder diagram that controls traffic in a four-way junction. So maybe like Uhuru Highway or Pennsylvania or whichever, but a junction that has four different ways. So this is the basis of your design. Now, this lab, there's no way you'll complete it in one session. One, it requires adequate preparation. Adequate preparation. If you don't prepare for this lab, you shouldn't even come to the lab. You will not get anything. It requires teamwork. This is the lab that tests you properly as to whether you work as a team or not. So it requires a lot of teamwork. and people who have ideas, and you float them and you check your colleagues for mistakes and so on and so forth. So you must have probably noticed this from your first semester lab. So what we have done, just like in the first semester lab, and you can get this from your colleagues who've done this already. Of course, I made available several things. One, I made available the lecture videos. You can get it from them. To just give you a brief overview of what PLCs are all about, I gave you, there's a data sheet for the PLC that we are using. And that PLC, I think, is Siemens, is it S2700 or S7200? I can't remember. I think it's S7200, yeah. So it's called Cymatic. Okay, so there's a data sheet for this, and the significance of the data sheet is, if, for example, I want to find a timer, so an on delay timer, an off delay timer, a retentive timer, whichever you want to use, you can go to the data sheet. It gives you a proper illustration of how to get that timer, how to connect it to your ladder diagram, and how to adjust its parameters. Because we know that timers are meant to count. So if you're asked for something of 50 Hz, you will have to do your math and know I can use a timer, and I give it a specific time to achieve the delay necessary for the frequency that has been requested. Okay, so therefore it is important that you look at the data sheet. There's also the link that I've given. You can ask your colleagues for the software. You can download freely the software for the Siemens software for simulator. So this is the simulator. Okay, to be able to simulate this. And so you can even do this from home also. You can try some of these concepts from home. So it is important you prepare adequately. It's important that you work as a team, but it is also important that you have a plan. Okay. The reason is, you will notice that there's a first segment, there's the first section, okay, where you'll have to do during your first session of the lab. Then you will, at the end of that session, there's some work that you must go and do. There's a design element that you must go and do. Then you come back for the other part. So the minimum amount of sessions that you can take for this lab is 2. That is, if you're actually prepared well, you're working as a team, and you have a plan, you will definitely need 2 sessions at the very minimum. Otherwise, you will go for more than 2 sessions. However, as you notice, we are nearing our exams. We might not have enough time for makeup sessions. So you really need to be serious, do your part, so that you complete this lab in the 2 sessions that is necessary, so that you don't have conflicting labs also, that you have to do makeups, and then you're also revising for your exams and all that stuff. So please take time, revisit these lecture videos, look at the data sheet, prepare adequately for the lab. If you're asked, because the lab is very interactive, if you're asked for homework, do that homework before you come to the lab. And usually Alice recommends that when you come to the lab, if there's homework, please write it down, come with your notebook, because you're also going to be recording values. Come with your notebook and write something down. Don't just come unprepared. So with these lecture videos and also the data sheet and the softwares, you're able to do something. And of course, the manual is there also to guide you on what is expected of you, plus the procedure is available there. What I want you to do is, for those who are having difficulties preparing for PLCs, there's a very good book that I'm using currently as a course book with the 5th year students. But it's very, very, I'm sure you probably will not get it online, but you need to speak to the 5th year colleagues. It's large, so I cannot send it via email. I had to find ways of sending it to your 5th year students. And so you can talk to your 5th year colleagues to send you. I'm sure you guys are connected, you know, their WhatsApp groups, their class reps and all that. Just get in touch, ask them for this book that is here, The Programmable Logic Controllers by Frank D. Petruzella. This book, I'm telling you, is going to help you a lot in understanding the PLCs, the basics. So the basics you'll just read quickly in chapter 1, okay? It will just give you the basics, and it's self-explanatory with illustrations. And I know that the book uses a different PLC from the one that you're using in the lab. In the lab, we are using Siemens, but this book uses the American version because it's an American guy who wrote this book, but it's using the Rockwell, what we are calling the Alan Bradley, the Rockwell company. So this is Alan Bradley. But the beauty is, if you look at Alan Bradley PLCs and Siemens PLCs, they are more or less the same. That is, if you're plotting their ladder diagrams, they have the same symbol for the normally open contact. They have the same symbol for the normally closed contact. They have the same symbol for the coil, that is the output. They have almost similar symbols for timers, okay? They have the same symbols. So let's say this is up count, so CTU. So the symbols or the notations that we use for Alan Bradley and Siemens are more or less the same. You will not see much difference. But the book has a very good illustration on how these components work and how PLCs work in general. So please take note of that. And the beauty is, once you do chapter 1, then you can go and do, I think it's chapter 4, where there are timers, because you're going to need timers a lot. Because remember, traffic light control is about timing, okay? So you can read chapter 1, where you get your introduction. Then you read chapter 4, very self-explanatory, where you're going to get all the illustrations on the 3 types of timers that we have: the up, the off delay, the on delay timer, the off delay timer, and the retentive timer. We see why you'll need a retentive timer. And then lastly, you can also do the part that has counters, okay? But there are even examples. I think it's in chapter 6. Chapter 6. So you're not reading all chapters, only specific chapters. In chapter 6, there is even a very nice illustration of how to design a traffic light junction. I mean, a traffic light PLC control for two-way junction, for a two-way junction. So and it's there with the ladder diagram, and it's very self-explanatory. So if you're able to understand this in preparation for your own design for a 4-way junction, it would be very easy, once you understand the 2-way junction, to simply scale it up to 4-way junction. Of course, you're not coping, because you'll find that there are certain requirements that are used in the 2-way junction that will not be required in the 4-way junction. But having understood the concept of how to design traffic light control for a 2-way junction, it shouldn't be difficult to now scale that up to a 4-way junction. Okay, so what I'm simply saying is, this book you'll find it very helpful in your preparation to be able to carry out the lab in the 2 sessions that are required. I've found it very, very helpful to me, and so I know with the way the content is presented and the language that is used there, you can quickly grasp the concepts on your own. Again, if there's a serious challenge that you're facing in your preparation for this lab, or even while you're doing this lab, you can always reach out to me. Just send me an email and tell me, this is what we have tried, this is where we are, and this is where we are facing a challenge. I'm really here to assist you. I'm not going to spoon feed you, but I'm going to assist you so that you are able to learn in the process. So feel free to ask wherever there is a challenge, but please prepare adequately. Take your time over the weekend, or whichever time it is, read properly around the PLCs. And that is for those who start with the PLCs. The PIDs are easier, simpler, because I want to believe you've done them in class already. Plus, the manual is giving you almost everything. You're doing almost just following procedures. But in the PLCs, you'll have to do your own design, and so you have to really have a plan, like I told you. So I want to end here, unless there is a concern or question or some direction that you need or clarification that you might want me to provide here before you start your labs. Today is Wednesday, so maybe you're starting your labs on Monday. So you should be having a lot of time to actually prepare for the next lab that you'll be doing. So that marks the end of my presentation, and I would like to ask for any questions at this point. Good. Not all of you attended this meeting, but again, that's usually how people are. We don't expect 100% turnout, but please share, because these are guys who are in your groups. So if they don't have this information, they will affect your performance, and they'll affect your efficiency as in regards to the work you'll be doing in the lab. So please share this information with them in good time, so they can also prepare, and so that when they come to the lab, they don't drag you down, so that you work together as a team. Okay? Because I see there are less than 8 people. So please ask everybody to prepare adequately for the lab.
Actually, we are
Yes, Marie.
16 and we were 17 in the lab. It's a list group.
Sorry, Marie, what did you say?
I'm saying in the attendance, we are almost all of us, since I can see we are 16 of us, and we are a total group of 17 students. The list group in
Good.
numbers.
Thank you. So if the class is fully represented, then that's great. All the best. I hope you can work as a team and be able to gather something out of this lab, and be very serious with it, because like I've told you, you're still going to meet the PLCs in 5th year. It's inevitable. So just be very serious, and you'll get something worthwhile out of this experience. Thank you very much. Enjoy your afternoon, and see you again next time. Goodbye.